My name is Michael Pendazis. This is Math 241, Probability and Statistics. These are the homework problems for test number 2. So this is in addition to the video lectures I'm posting on YouTube. I'm posting this video to go over the homework with you for test 2. Okay, let's get started. Alright, so on the homework sheet, right, this is the homework sheet I gave all of you in person. It's also on Blackboard in the content folder, so you can find that there also. We're going over the problems in chapters 3, 4, and 5 on the sheet. Okay, so let's look at 3.1.1. It's pages 76 to 77, and it's exercises 1, 2, 6, 7. But I'm not going to do all of them. I'm going to, let's look at number 1. Let's look at the easiest one. Okay? So open your book and look at the problems with me. Number 1 says a box contains 10 red. There's 10 red, 10 white, 5 blue balls. Okay? A ball is chosen at random from the box. If the ball chosen is not blue, what is the probability that it is white? So you want to know the probability that the ball is white, given that it is not blue. Okay? So if the ball chosen is not blue, what is the probability that it is white? It's asking for the probability of white given that it is not blue, right? And so in the section 3.1, we learned that the probability of A given B is equal to the probability of A and B over the probability of B. This is also N sub AB over N sub B. N sub AB is the number of outcomes in event A and B, and this is the number of outcomes in event B. Okay? Right? If you have N sub X, it's the number of outcomes in event X. Right? And an event is a subset of the set of simple outcomes. Set of outcomes, right? So N sub AB is the number of outcomes in event A and B. N sub B is the number of outcomes in event B. Okay, so probability of A given B is the number of outcomes in the event A and B over the number of outcomes in B. So this is the number of outcomes in which you choose a white ball that is not blue over the number of outcomes that are not blue. Okay? So we have the event of choosing a white marble and the event of not choosing a blue marble. And so the probability of choosing a white marble given that you did not choose a blue one is the number of simple outcomes that are white that are not blue over the number of simple outcomes that are not blue. And so there are 10 white balls, and they're all not blue, so that's 10, divided by the number that are not blue. 10 red, 10 white, 5 blue. There are 20 that are not blue. So 10 over 20, that's 1/2, or 0.5. So 0.5 is the probability of choosing a white ball given that you did not choose a blue one. Okay? And so that's the answer to number 1 in this section. Okay? So there's 15 sections I'm going to go over. So I'm going to do one problem each section. Okay. I'm going to try to focus on the easier ones. That way I can get you started. Okay? 3.2, pages 85 to 87. So you can go to your book to those pages now. And then exercises 1, 2, 5, 9. Okay. Okay, so for page 85, okay, so let's look at number 5. So there's a lot of information for number 5. It says let A, B, and C be events, and then it gives a whole lot of information. So I'm going to summarize this here. A, B, C are events, subset of the sample space. P of A is equal to 0.4. P of B is equal to 0.5. Probability of event C is equal to 0.6. And P of A and B, which is abbreviated PAB, is equal to 0.1. And the probability of B and C, which is abbreviated PBC, is equal to 0.2. P of A and C, abbreviated P of AC, is equal to 0.3. And P of ABC, probability of A and B and C, is equal to 0.02. And so the goal is to find, in part A, we want to find the probability of A given B. Okay? So probability of A given B. That's the probability of A and B over the probability of B. Probability of AB is 0.1 divided by the probability of B, which is 0.5. That's 1/5, which is 0.2. Part B, probability of A given BC. And so this is the probability of A and BC, which is ABC, probability of ABC over the probability of BC. The probability of ABC is 0.02 divided by the probability of BC, which is 0.2, and that's equal to 1/10. And that's equal to 0.1. Part C, the probability of AB given C, and that's equal to the probability of ABC over the probability of C, which is probability of ABC is 0.02 divided by the probability of C, which is 0.6. And so that's equal to 1/30. And so that's equal to 0.003, about the nearest thousandth. Because 1/10 would be 0.1. That's 1/3 of that. So it's about 0.033. Yeah. So it's the nearest thousandth is 0.033. So part D is probability of A union B given C. Okay? So probability A union B given C is the probability of A union B and C over the probability of C. And by using, and so we can simplify probability of A union B and C as the probability of AC or BC over the probability of C. Okay? If you have 3 events, A, B, and C, this Venn diagram here, then A and C would be here, and B and C would be there. Okay? And so if we wanted probability of AC union BC, we would just take the probability of AC union BC is equal to the probability of AC plus the probability of BC minus the probability of ABC. Because when we take this intersection and this intersection, we're counting the middle part twice. See this little intersection part here? If we take this and this, this overlaps twice. We need to get rid of one of them, and that's the probability of AB. That's ABC. And so, so that's equal to the probability of AC, which is 0.3, plus the probability of BC, which is 0.2, minus the probability of ABC, which is 0.02. And that's equal to 0.5 minus 0.02, which is 0.48. So 0.48 is the probability of AC union BC. That's 0.48 divided by the probability of C, which is 0.6, or 0.60. And so then that's equal to 4/5. And that's equal to 0.8. Because there's 12, there's 4 12s and 48, and there's 5 12s and 60. So it's 0.48 over 0.60 is 4/5, and that's 8/10, which is 0.8. Okay, and that's part D. So there's more parts. It goes up to J, but let's stop there, and you can do the rest of them, hopefully. Okay, and so that's a problem in 3.2. Okay, so now 3.3.2. Pages 92 to 93. Numbers 1, 2, 6, 8, 13. Okay? So these are the problems in section 3.3.2. And so for this one, okay, so let's look at number 2. Okay, so for number 2, reading the problem on page 92, it says use the property of independence to find the probability of getting only even values in 5 rolls of a balanced die. Okay, so you're going to roll a die 5 times. This will be the first one. That's the second one. This is the third one. Every time I draw a cube, I'm going to start off drawing it a different way. It's for fun. Okay, and then let me just end it with the easiest way to do it that way. Okay, so these are the 5 die, and each one has numbers 1 through 6. Okay? So you have the possibility of 1 through 6 in each roll of the die. And so what we want to do again is to use the property of independence to find the probability of getting only even values in 5 rolls of the die. So these are all the possible outcomes, right? But the even ones are 2, 4, and 6. And so we want to find the probability that each roll of the die, we get 2, 4, or 6, when we could possibly get 1 through 6 each time, right? And so the probability of only evens, right, for the 5 rolls of the die, is going to be the probability of only even in the first roll times the probability of only even, probability of even in the first roll times the probability of even in the second roll times the probability of even in the third roll times the probability of even in the fourth times the probability of even in the fifth roll. Okay, so I abbreviated, right? So the probability of only evens in all 5 rolls is probably even in the first roll times and so forth. The probability of even in the first roll, well, there's 3 evens, right? So it's the number of evens divided by the number of possible rolls, right? So the probability of even number is the number of even outcomes over the total number of outcomes. And so you just multiply that by itself 5 times. Okay? So I don't want to. Right, so the last one. Number of evens over the number of possible rolls. And so the number of evens is 3 divided by total number of possible rolls, which is 6. So the probability of even on the first roll is 3 out of 6. The probability of even in the second roll is 3 out of 6. The probability of even on the third roll is 3 out of 6. The probability of even on the fourth roll is 3 out of 6. Probability of even on the fifth roll is 3 out of 6. They're each 1/2. This is 1/2 to the 5th power, which is 1 over 32. And so the probability of only evens in all 5 rolls is 1 over 32. Okay? Okay, and so that's number 2. And so used independence. Probability of A, B is equal to probability of A times the probability where A and B are independent events. Okay. That's the definition, right? Independent events. Okay. So that's 3.3.2. 3.4. We go pages 95 to 96. And it's going to be, in this section, I gave you one problem. Suppose that in example 3.14, 4 points are required to win. Okay, so 4 points. Okay, so, sorry, I was just thinking for a minute. So for number 1, we have to look at example 3.14, right? And 4 points are required to win. Okay, so 4 points are required to win. Okay, and so, and we're going to say that in part A, I'm going to do part A. Okay, if a game were terminated, the game is terminated when one player has 3 points. Other has 1 point. How should the stakes be divided? Okay, so the game is terminated when one player has 3 points and the other has 1 point. How should the stakes be divided? So basically what that means is you need to have 4 points to win, right? Each round, one of the players wins a point. And they're both equally likely to get that next point. Okay, so each player is equally likely of making a point in each play. Okay, so let's say player 1 has 3 points. Let's say player 2 is a player with 1 point. Okay, and so what we're going to ask is how should the stakes be divided? Meaning, what's going to be the probability of each player winning at this point? Okay. So player 1 has 3 points, player 2 has 1 point, and 4 points are required to win, right? 4 points. And so that means player 1 is 1 point away from winning, and player 2 is 3 points away from winning. Okay? So how should the stakes be divided? Well, let's find the probability, not that player 2 wins, but let's find the probability let's not find the probability player 1 wins, even though he's 1 point away. Let's find the probability player 2 wins. He or she has 1 point, and he or she needs 3 more points to get to 4 points. But what's important about player 2 is that player 2 has to win every game to this point, because if player 1 ever wins any of the next points, player 1 wins. So in order for player 2 to win, player 2 has to win every other point. And so what's the probability that player 2 wins given the situation above? Right? That player 1 already has won 3 games and player 2 has only won once. Okay? Well, that would be the probability that player 2 wins 3 consecutive games. 3 consecutive points. Okay? And well, what's the probability that player 2 wins 3 consecutive points? It's the probability that player 2 wins a point raised to the 3rd power, right? Because I'm just multiplying that by itself 3 times. And so that probability is 1/2. And so it's 1/2 cubed, which is 1/8. So the probability that player 2 wins in this situation is 1/8. And so that means that the probability player 1 wins in this situation is 7/8. Okay? And so the probability that player 1 wins, not from the beginning, but given the situation above, is 7/8. So the probability player 1 wins in this situation is 7/8, and the probability player 2 wins is 1/8. And so we can split the stakes 7-1 in favor of player 1, because player 1 has a 7/8 chance of winning and player 2 has a 1/8 chance of winning. And so we can split the stakes 7-1 in favor of player 1. Player 1 is 7 times more likely to win. 7-1. Okay? Even though they each have a 50% chance of getting any point, the lead that player 1 has, having 3 points as opposed to player 2 having 1, gives him now he's now 7 times more likely to win the entire the whole thing, get 4 points. Okay? And so part B is very similar. And so that's 3.4. Okay. Pages 98 to 99. Okay, so on page 99, number 1, we suppose, okay, so for 99, it's 98 to 99, so it's actually page 98. Oh, wow. This is a long problem. Okay, so then applicants for employment at a certain large firm are initially interviewed by any one of 3 personal officers. If an interview is favorable, the applicant is given a written test. If the applicant's test result is favorable, he or she is interviewed by a technical staff member. A favorable report from the technical staff member places the applicant on a waiting list for the next job opening. The following statistics are known concerning the application process at this firm. So personnel officers, A, B, and C interview 40%, 35%, and 25% respectively of the applicants. Okay, so I'm just abbreviating all this. Right? The personnel officers A, B, and C interview 40%, 35%, 25% of applicants respectively. Okay? Okay, and so then these same personnel officers, they give favorable reports to 60%, 75%, and 80% of the applicants. So these are favorable reports. That percent of applicants. Okay, 10% of applicants to take the written test get favorable results. So you read the plus sign. And of those, 30% get a favorable report, which I'm really positive, from the interview with the technical staff member. And so in part A, we're going to draw a tree diagram of the empirical probabilities defined by these statistics. Okay, so first there's an interview, right? There's the interview here. I'm going to try to visualize this myself easier. There's an interview between the personnel officers A, B, or C. After that, if the test is favorable from that interview, there's then a written test. Okay? Now, if the test result is favorable, which I'm going to abbreviate for that plus sign, then it's an interview by a tech staff member. Okay? And then, if there's a positive from that, on the waiting list for the next available opening. Okay, so draw a tree diagram. This is not the tree diagram. This is just to help me draw the tree diagram. So let me write A over here. So first, we're going to start at the beginning here. And now there's going to be an interview among one of three. You're going to be interviewed by A, B, or C, the personnel officers. Then, depending on that interview, so A interviews 40%. So the probability that you go along here is 0.40. The probability here is 0.35. The probability here is 0.25. Right? That's the probabilities of being interviewed by A, B, or C. Then the written test. Then, if you're interviewed by A, there's a 60% chance that's going to be favorable. If that happens, you continue. Because if you get a favorable interview from A, B, or C, you then go to the written test. And now the written test I'm going to put by a W. The W is the written test. And now, okay, so then here, there's a 75% chance, 0.75 chance, that it's positive for an applicant from B. And then there's a 0.80 chance that the interview is positive from C, which brings you to the written test here. 10% of applicants that take the written test get a plus. So this is 0.10. And then of these, and then after the written test, if it's positive, you go to the tech staff interview, which I'm going to abbreviate by T. As this is 0.10 also for everybody here who gets the written test. They all have a 10% chance of moving on from written test to the technical staff interview. And then 30% get a plus from the tech staff, and so then that means that there's a 0.30 chance that you then go to the waiting list, and I'm going to call the waiting list L. So there's a 0.30 chance you get a positive from the tech staff here, and you go to the waiting list there. So this is the tree diagram for this problem. This is the tree diagram. Okay, and so you can use this to find the probabilities of different events. Okay? So that's part A. So part B says what percentage of all applicants are eventually placed on the waiting list for employment? Okay, so in order to get to the waiting list, right, this is the way, so you just have to determine from the beginning, right, from the very beginning, there's three ways to get on the waiting list. You could be interviewed by A, B, or C in the beginning, and then those people who pass will take the written test, the technical test, and then be put on the waiting list, right? So the probability that you get interviewed by A and you get on the waiting list is 0.4 times 0.6 times 0.1 times 0.3. That's the probability of the product of these probabilities of probability being interviewed by A and getting on the waiting list. That's plus the probability of being interviewed by B and getting on the wait list, which is 0.35 times 0.75 times 0.10 times 0.30. That's plus the probability of being interviewed by personnel officer C and getting on the wait list, which is 0.25 times 0.80 times 0.10 times 0.30. And so you multiply those out and you add those up, and you get 24, 72, 24, 72, then there's 4 decimal places. So it's 0.0072. 24 times 3 is 72, and 4 decimal places, so 0.0072, plus this times this. So 3 times 35 is 105, right? 3 times 35 is 105. 105 times 75 is 7,500. 7,500 plus 375. 3875. So that's 3875 with 6 decimal points. 3875 with 6 decimal points. So that's 0.003875. That's the product of that. Let me just make sure. 3 times 35 is 105. 105 times 75 is 7,500 plus 7,500 plus 105. 75, 105, 7,500. Yeah, good. Okay, so it's 0.007875. My bad. I misspoke there. That's a 7 there. And it's plus, and then these 4. This is easier. 8 times 25 is 200. 200 times 3 is 600. So that's 600. So that's 600 with 5 decimal places. 600 with 5 decimal places. So then it's 3. That's 200, 600, 2, 4, 5 decimal places. Good. So that's 0.00600, or just 0.006. And if you add those up, you get so there's a 75 there. And then there's a 4 here, and there's a 0 there, 15, 21. So you get 0.021075. That's the probability of being on the waiting list. Right? So the less you use your calculator, the better. Okay. So then 75 is 4 here. It's a There's a 1 there. 15, 21. Good. Alright, so it's 0.021075. Okay, and so part C, I'll leave that up to you. Okay? So that's number 1 in 3.5. Okay, you can pause the video to look at the tree diagram or anything else. Okay? Okay. Next. Okay, so that's chapter 5. 3. That's chapter 3. Okay, so chapter 4. So the first one, 4.2, pages 105 to 106. numbers 1 and 3. Okay? So 4.2, 105 to 106. Okay, so let's look at number 3. Okay, so the possible ratings of a certain music test are 1, this is on page 106. The possible ratings on a music test are 1, 2, and 3. So the ratings on music test are 1, 2, and 3. Suppose that the 3 students selected at random take this test and X is the average test score. Okay, so 3 students take the test. X is their average test score of 3 students. Part A, use a notation of functions to define the random variable X. Okay, so the hint is to use this notation. IJK is the notation for the outcome of the first, second, and third students receiving the IJK ratings, respectively. Okay, so the notation in the hint that the book suggests you use is that this 3 tuple represents the outcome of the first student getting an I in this rating, the second student getting a J, and the third student getting a K, where I, J, and K are either 1, 2, or 3. And so if X is the average test score, then X of the outcome I, comma, J, comma, K is just you add up the 3 ratings, I plus J plus K, and divide it by 3. And that's the average of the 3 test scores I, J, and K. I plus J plus K divided by 3. Okay, and so that is the answer to part A. And then part B is use a table of values to define the random variable X. Okay, so we'll use a table of values to define X. So let's see. So here on the first column, I'm going to put the outcomes I, J, K. These are all the possible outcomes I, J, and K, where I is 1, 2, or 3, J is 1, 2, or 3, K is 1, 2, or 3. And then the next column is going to be the value of X at that outcome. And so the first outcome we can think of is just 1, comma, 1, comma, 1. Next outcome we can think of is 1, comma, 1, comma, 2, 1, comma, 1, comma, 3. Next one is 2, comma, 1, comma, 1, 2, comma, 1, comma, 2. And actually I'm going to erase this now from A. Erase A. I accidentally erased part of the question. Average test score. Students take test. Good. Okay, that's good. And then 2, 1, 3. And 1, 1, 1, 1, 2, 1, 1, 3. Oh, wait. Sorry. 1, 2, 1, 2, 2, 1, 2, 3. 3, 9, 27. Okay. And then this is going to be 1, 3, 1, 1, 3, 2, 1, 3, 3. Okay, yes it is. Okay, and then that's one starting with 1. There's 9 of them. It's going to be 9 that starts with 2. I'm going to split this up into 3 different tables. Okay, this table is going to be for these outcomes. This is going to be I. I'm going to continue the table here. 2, comma 1, comma 2. 2, comma 1, comma 3. 2, comma 2, comma 1. 2, comma 2, comma 2. 2, comma 2, comma 3. 2, comma 3, comma 1. 2, comma 3, comma 2. 2, comma 3, comma 3. There should be 9 there. 3, 6, yep. And then the third subtable, I, J, K in the first column, X of I, J, K in the second column. And so now this is going to be starting with 3, 3, 1, 1, 3, 1, 2, 3, 1, 3, 3, 2, 1, 3, 2, 2. Last off, 3, 2, 3, 3, 3, 1, 3, 3, 2. Okay? Okay, so now these are all 27 possible values of outcomes for I, J, and K, where each of I, J, and K are either 1, 2, or 3. And then X is the average for each of those 27 outcomes, right? So the average, if they're all 1s, is 1. The average of this is, you just add them and divide by 3, right? Because in part A, we found that X of I, J, K is equal to I plus J plus K divided by 3. So we're just going to add them up and divide by 3, and that's the average. So add these up, 3 divided by 3 is 1, divided by 4 over 3, 5 over 3. Sorry. 4 over 3, 5 over 3, 6 over 3, 5 over 3, 6 over 3, 7 over 3. Over here, we have 4 over 3, 5 over 3, 6 over 3, 5 over 3, 6 over 3, 7 over 3, 6 over 3, 7 over 3, 8 over 3, 5 over 3, 6 over 3, 7 over 3, 6 over 3, 7 over 3, 8 over 3, 7 over 3, 8 over 3, 9 over 3. Okay? So those are all the probabilities of all 27 of them. You just add them up and divide by 3. Okay? And that is defining the random variable x using a table of values. The table tells you for all 27 outcomes of the experiment what the value of the random variable is for all 27 outcomes of the experiment. Okay? It's the average of 3 numbers in the 3 type. Okay, and so that's number 3 in 4.2. Let's keep going. Okay, so next, after 4.2, is 4.3, page 109 to 110. So 4.3, page just 109 to 110, numbers 369. Okay, so let's look at number 6. Okay, so for number 6, in page 109, it says a box contains a penny, 2 nickels, and a dime. There's the box. It contains 1 penny, 2 nickels, and 1 dime. If 2 coins are selected at random from the box, so we're going to select 2 coins at random. This is a penny, this is a nickel, this is a dime, okay? 1 penny, 2 nickels, 1 dime. Okay, 1 dime, and I'm going to select 2 coins at random. So if I select 2 coins at random from the box, and x is the sum of the values of the 2 coins. X is the sum of values of 2 coins selected at random from the box above. Right? What is the probability function of x? Okay? So what is the probability function of x? Well, x's are discrete random variable, okay? It's discrete because there's finitely many values for x. We'll see that, okay? So if we choose 2 coins, what are the possible 2 coins we could select? These are the possible 2 coins to select. We could select a penny and a nickel. You could select a penny and a dime. That would be if we selected 1 penny. It would be a penny and a nickel or a penny and a dime. If we selected a dime, we already selected a penny with that, but we could select a nickel with the dime. Right? So if we selected 1 dime, that dime would either be with the penny we already wrote down or with a nickel, which we didn't write down. So that would be if there was 1 penny or 1 dime. If there was neither, we would choose 2 nickels, and so both coins would be a nickel. And so these are the 4 possible ways we could pick 2 coins from that box. A penny and a nickel, a penny and a dime, a nickel and a dime, or a nickel and a nickel. And if you add up those values, in each case, you're going to get 6 cents here, you're going to get 11 cents here, you're going to get 15 cents there, and you're going to get 10 cents there. And so these are the amounts, right? The amount of cents in each case. So if you pick a penny and a nickel, you get 6 cents. You pick a penny and a dime, you get 11 cents. If you pick a nickel and a dime, you pick 15 cents. And you pick a nickel and another nickel, you get 10 cents. So these are the possible values of x, right? X is the sum of the values of the 2 coins selected at random from the box above. So the only values x can take are 6, 11, 15, or 10. Okay? So the question, again, is for number 6, is what is the probability function of x? Well, then the question is, right, what is the probability that x is equal to 6? What is the probability that x is equal to 10? What is the probability that x is equal to 11? And what is the probability that x is equal to 15, right? So the amount of money you select from the box can only be 6, 10, 11, or 15 in increasing order. And so the probability only has a non-zero, possibly non-zero value when x is 6, 10, 11, or 15. If you consider any other value of x, the probability is 0, because you cannot take that much money given this problem, right? So these are the only possible values of x that would have non-zero probability. Okay? So what is the probability of each? What is the probability that you get 6 cents? Well, 6 cents corresponds with choosing a penny and a nickel. And so what's the probability if you choose 2 coins from this box that you chose a penny and a nickel? Well, so it would be, so the probability of x equals 6 is the probability of choosing it would be, so if we found the number of ways you can choose 1 penny and 1 nickel, then there's 1 penny and 2 nickels, so there's 2 ways. That would be divided by the number of total ways you could choose 2 coins from that list, from the box. And so if there's 1 penny, 1 dime, and 2 nickels, you'd have to choose 2 of them. So there's a penny, 2 nickels, and a dime. Then the number of ways to choose there's two, okay, right, there's two ways to choose a penny and a nickel. Penny in this nickel and a penny in that nickel. And some ways to choose any two coins would be, you have 4 choices for the first coin, because there's 4 coins, and there's 3 left for the next coin. Oh, okay. So there's four coins, 4 factorial divided by the 2 factorial because there's two of them are the same. 2 of them are nickels. So you have 4 coins. Wait, sorry. It's 4 times 3 over 2 times 1. Because there's 4 coins, so you have 4 choices for the first coin, then 3 for the next coin. But you have to divide it by 2 times 1 because there's 2 coins that are the same. So you have to divide by 2 because 2 are identical, and so you're actually counting twice. Every time you choose one nickel, you could have chose the other, but they're considered the same. So you have to divide by 2. So this is 6. There's 6 total ways to choose 2 coins from that list, and let's see if that makes sense to me. 1, 2, 3. Yeah, there's 6. Okay, that works. Sorry. So there's 6. So it's 2 out of 6. So 2 out of the 6 ways are choosing a nickel and a penny. To choose 10 cents, it's 2 nickels. There's only one way to choose 2 nickels. That's 1 out of the total 6. 11 is if it's a penny and a dime. And there's one way for that, just a penny and a dime. And then the 15 cents is a nickel and a dime. There's 2 nickels, so each nickel could be with the dime. There's 2 of those. That's 2 out of 6. And this works because 2 6 plus 1 6 plus 1 6 plus 2 6 is 1. And that's good. So the probability that when x equals 6 is 2 6, which is 1/3, which is 0.33. The probability x equals 10 is 1 6, which is 0.16. 0.1. I'm going to round to near 1,000. 0.166. 0.167. Okay, round it to nearest thousands, that's 0.167, and this is 0.333. Okay? So that's the probability that the discrete random variable takes any non-zero number. And so the final answer, what is the probability function of x? The probability that our discrete random variable x, capital X is equal to little x, is equal to 0.333 if little x is equal to 6 or 15. It's equal to 0.167 if little x is equal to 10 or 11, and it's equal to 0 elsewhere. So any other value of x, the probability that capital X equals that little x is 0. Okay, and that's the final answer for number 6 and 4.3. Sorry. Okay, so 4.4, page 111, exercise number 3. Okay, good. Okay, so 4.4, page 111, number 3. So for number 3, it says draw a histogram and a bar chart of the random variable x in example 4.3. Okay, so it's histogram and a bar chart. I'm going to do the bar chart first. So for number 3, histogram and bar chart, example 4.3. So in example 4.3, there's 3 flips of a coin, of a regular coin, right? And so there's 3 coins, and the possibilities are heads or tails for each coin. And the discrete random variable x is the number of heads in the 3 flips. Right, so that means that the possible values of x are 0, 1, 2, or 3. Right, because x is the number of heads in those 3 flips, and so if you flip the coin 3 times, the number of heads is 0, 1, 2, or 3. Okay, and then it says, it's found in that example that the probability that x is equal to 0 is 1/8. Probability x is equal to 1 is equal to 3/8. Probability that x is equal to 2 is 3/8. And the probability x is equal to 3 is 1/8. Okay, and so we're going to just draw a bar chart for that situation. So here's the bar chart. Here. So we have f of x here, and we have the value of x here, right? This is the number of heads. Okay, and the probabilities are on the side. So I'm going to go by eighths. So it's going to be 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. We won't need that many eighths. This is 1/8, 2/8, 3/8. The rest won't matter, so maybe we should. Alright, anyway. Okay, so then. Okay, so then 0, 1, 2, 3. So if there's 0 heads, the bar will go up to 1/8. So 1 is 3/8. 2 is 3/8. And 3 is 1/8. Okay? And so that bar chart is telling you the number of heads. For each number of heads when it's 0, the probability is 1/8, 1, 3/8, 2, 3/8, 3, 1/8. Okay, and so this is the bar chart. Okay? And then the other one is the histogram, the probability histogram. And so for the probability histogram, it's almost exactly the same. But then I'm going to make the probabilities, okay, still 1/8. This is going to be f of x. This is going to be x, which is the number of heads. It's going to be 0, 1, 2, 3, 1/8, 2/8, 3/8. And for 0, it's going to be that. 1, it's going to be that. Right, for 1, it's 3/8. There we go. So now that's the probability histogram. Okay, so here's the probability histogram for this discrete random variable, and this is the bar chart for that discrete random variable. So that's 4.4, number 3. Okay. Okay. So 4.5.5.4 is the next section, and it's pages 130 to 133. And the numbers are 5, 9, 14, 19, 24. Okay, so if we go to page 130, let's look at Let's look at number 9. Okay? So for number 9, so remember number 9, it says a quality control inspector examines 10 out of every shipment of 1,000 packages of frozen chicken for spoilage. Okay? So there's 1,000 packages. Okay, so we're going to examine 10. Okay, so examine 10 out of a shipment out of every shipment of 1,000 packages. The quality control inspector. The shipment is approved if and only if all 10 packages pass inspection. Okay, so all 10 need to pass inspection for a shipment to be approved. Find the probability of a shipment being approved, even though 10% of the packages are badly spoiled. Okay, so if 10% is badly spoiled, that means that 100 of those 1,000 are badly spoiled, and 900 are okay. Okay? So 100 are badly spoiled, 900 are okay. And, okay, so, so 10 have to be approved, even though 10% are badly spoiled. Okay, so in order for the probability of the shipment approved, that means the probability the first is approved times the probability the second is approved, we're going to check to abbreviate that, times ... times the probability the 10th is approved. Okay, so the probability the first is approved, it's just there's 900 out of 1,000 that are good. And so now, if that one was approved, then that means 1 out of the 900 are no longer able to be considered, and so there's 899 out of the total 1,000 left. Then there's 898 over 1,000 times ... times. Now the 10th one, when you check the 10th one, there's 9 that were already considered. So it's 891 out of 1,000. Okay, so you multiply those out, and that's the probability the shipment is approved. Okay? Alright. So that's section, so you multiply that out, and then get the answer. So that's chapter 4, and the problems, some of the problems from there. I'll put up another video where I talk about more problems in chapter 5 and some other stuff. Okay? So have a good day. See you soon.